Good afternoon, Professor. My name is Arturo Gutierrez, and I just took, or I'm taking, Quiz 1, Module 1, Quiz 1. So it's a total of 3 sheets. This is sheet 1, sheet 2. So sheet 1 and sheet 2 go together. They're both question 1. And then the third sheet, I put the answer for question 2 and for question 3 also. So we can start with question 1. So for this one, we had to prove that the cross product and the dot product all equaled each other. These do all equal each other. If you're looking at my solution, I solved all of them. So I did the cross product for each one. So just for example, the first one I did the cross product of B and C, and then I dotted it with A. I did the same for all 3 of them. So because they're all equal, these are all the solutions are supposed to equal, but I think I may have made a mistake with my signs, because I think something's supposed to cancel so that they are all equal solutions. But nonetheless, the theory behind these is when you do the cross product. So for the example, the first one, the cross product of B and C, that's going to give you the area. Those 2 vectors will give you the area. And then when you take that and you dot it with A, that'll give you the height. So in total, it'll actually give you the volume of, I think it's a parapiped. The shape, it's like almost looks like a leaning rectangle. So it's going to give you the volume. So regardless whether you do, cross product of B and C, or A and C, or C and B, and then you dot it with A or B or C, they're all going to result in the same volume. The only difference is if you're looking at them in a 3D projection, obviously it'll appear in a different plane, right? Because if you cross B and C, it'll be in the B and C plane. Or well, not in the B and C plane, but it would be in the corresponding, which would be in the what is it, J and K plane, I believe. I may have gotten that confused, but nonetheless, all 3 of them equal each other because all 3 of them will give you the same volume, the same numerical value, the same answer. So that's my theory behind question 1 and how I answered question 1. So next we can go to question 2. So for this one, in the lecture notes, you actually gave us the equation. So A dot B is equal to the magnitude of B times the magnitude of A cosine of A, which A is the angle. So you asked us to solve for the angle, which in this case would be angle A. So what I did here is I basically took the equation you gave us. I dotted A and B, and I set that equal to magnitude of A, magnitude of B, cosine A, because we can do inverse cosine to give us that angle A. So in essence, I took the equation and I just solved for A. So if you set that up, you can see by my solution set, you get the dot product of A and B, and then you're going to divide that by the magnitude of A and B, and then you're going to take the inverse cosine of that, which is going to give us an angle of 20.92 degrees, and then I just rounded to 21 degrees for the angle between those 2 vectors. For number 3, you asked us to compare the Bingham fluid to a Newtonian fluid. So I did put the description in the answer box. and then I drew the graph on here. So looking at the graph, I can explain the graph. So looking at the graph, so a Newtonian fluid is one that follows the Newton's law of viscosity. So a Newtonian fluid, regardless of the amount of stress that it, impacts or incurs, the viscosity is not going to change. Now, a non-Newtonian fluid, those fluids, when they receive, a certain amount of stress, the viscosity will change. So a Bingham fluid or plastic would fall under a non-Newtonian fluid. And the main difference between those two is, for example, like I mentioned, a Newtonian fluid, those, regardless of the amount of stress, the viscosity is not going to change. Now, a Bingham fluid, when you're looking at the graph, the reason that it's above a Newtonian fluid is because a Newtonian fluid, for instance, even at very low levels of shear stress, it's going to begin to deform. So that's why you can see it at the well, not the peak, but the very bottom, and it starts to progress as stress increases, even at a very minimal level. As soon as it receives any sort of stress, it's going to deform, and it'll actually deform under stress conditions that are under the yield stress. So the yield stress is the point where a material will start to deform. So as you can see, a Newtonian fluid takes very minimal stress to deform. Actually, stress under the yield point, it will cause it to deform. Now, a Bingham fluid is basically the opposite. A Bingham fluid, it needs to be incurring stress above the yield point. So if it incurs stress below the yield point, it's not going to deform. That's why when you look at the graph, it actually begins, at a certain height on the stress axis, because it needs to be at a level above its yield point in order for it to start to deform. And that's the same reason that a Bingham fluid can act as a rigid body, and a Newtonian fluid, will not act as a rigid body. So a Bingham fluid, it acts as a rigid body up until the point where the yield stress is met. So a good example that made it very easy to visualize would be like mayonnaise or mayo. If you dump mayo on the table, it'll sit there almost, act like a rigid body. Or even Jello. I think Jello is a better example. You put Jello on there, it'll act as a rigid body. It's not going to disperse or go everywhere up until you take, maybe say, a spatula or a knife or a butter knife, and you apply stress to that. Then it will flow like a Newtonian fluid. But again, it will only flow at that point because you're applying stress, and that stress is stress above its yield point. When it's just sitting on the table, the stress that it's incurring from, let's just say, from the surface, the shear stress, it's, like I said, it's not at its yield point in order to cause deformation. So that's the difference between a Bingham fluid and a Newtonian fluid, and also why on the graph, right, they both increase linearly, so they increase, proportionally, they deform proportionately to the stress. But a Bingham fluid, starts at a certain level of stress because it starts basically at its yield point. So those are the three questions. Thank you.